I would like to attention. I have some short announcements. First of all, for newcomers, for participants of Brazilian school, lunch. So we're having lunch all together upstairs near swimming pool. And those who are new, so you just come and there will be a person and you mark your name. He has a list of all participants, so you just point to him name. It's going to form some queue, but it's moving fast. And second thing, also for newcomers, Augusto Teixeira, can you raise? So he's running student seminars as if we don't have much what to do. And usually they run from 2 to 30 to 45. So if you want to present your work, please contact Augusto and it will be announced. Okay, and now it's my great pleasure to present Gordon Slade from University of British Columbia, and he is going to give second talk of the school on self-avoiding walks.
Thank you very much. First, I'd like to thank the organizers for giving me an opportunity to speak to you, but more than that, for organizing this magnificent event, which is now entering its 4th week. I've learned a lot of things by listening to the lectures. I also had to unlearn one thing, which was that I had this image that Brazil was kind of a laid-back country. And after these last 3 weeks, I've been cured of that misconception. So Frank has given an introduction to what I want to say in the last 10 minutes of his talk this morning. In fact, my first lecture will basically be those 10 minutes expanded to an hour and a half. But before I get started on that, let me say something more general about how the course is going to go. So the plan is going to be the following. First lecture will be introductory, in which I will say some of the basic things about the self-avoiding walk model and some of the open problems, which we'll come to rather quickly. In the second lecture, I'll talk about the Hammersley-Welsh bound. So this is a bound from 1962 on the number of n-step self-avoiding walks that remains the best known rigorous bound now 50 years later. And it uses a number of interesting ideas that I think are worth recalling. So that will be the second lecture. And then the third and the fourth lectures will be about the lace expansion and how it applies to study self-avoiding walks in dimensions d greater than or equal to 5. The fifth lecture will be about integral representations for the self-avoiding walk. So these are ways of taking a self-avoiding walk problem and writing them as a kind of field theory with bosons and fermions, which sometimes sound like intimidating words if you don't know what they are, but actually you'll see that it's not a difficult concept to write down some exact identities that map the self-avoiding walk problem onto a problem that looks more like a problem in field theory. And then in the last lecture, I will show you how to use the integral representation to tackle the self-avoiding walk problem in 4 dimensions using renormalization group methods. Now, I don't have any lecture notes written up for the course, but if you go to my web page, you'll find that there are references there, usually with links, for all of these topics. So you can read about it there. Then there'll be some tutorials. So the tutorials will be led by Roland Bauerschmidt and Jesse Goodman. Can you stand up so people can see who you are? Who are graduate students at the University of British Columbia. And the first tutorial will be some elementary facts about self-avoiding walks and actually also about simple random walks, transients and recurrence of simple random walks. The second tutorial will not be a tutorial. It'll be a lecture by Hugo Dumenil. about his very interesting recent paper with Stas Smirnov showing that the connective constant for two-dimensional self-avoiding walks on the hexagonal lattice is equal to the square root of 2 plus root 2. So that will be on tomorrow. And then, well, tutorials 3 and 4, naturally enough, will be about the Lace expansion. And we'll give a different approach to the Lace expansion than what I'll actually be talking about in the lectures. This will be the original approach of Bridges and Spencer. I'll do it in a different way in the lectures. And then the 5th tutorial will be about what's called the Simon-Leib inequality, which is something that we need in order to deal with self-avoiding walks in the infinite lattice as by approximating by a finite lattice. And this is a concept which, as I say, is going to come up in the 5th lecture, but it's also something that's worth knowing about in general because it applies in spin systems. That's where it was originally introduced. It also applies to percolation, and it's just something that's good to know about. So in that tutorial, you would have a chance to see something about that. There are sheets for the tutorials that are, well, they're available on my webpage, but they're also available out here, hard copies. So you can pick those up for the tutorials, which, by the way, are going to follow the same sequence as the lectures. So the lectures are alternating. Frank started today, I'll start tomorrow, and the tutorials will follow the same sequence. So it'll be random polymers first today, and then self-avoiding walks second. All right, so I guess I'm ready to start now, and we'll be working on ZD, and D is a positive integer, and we're interested in particular in how the effect of the dimension will change the behavior of the walk. And before I come to self-avoiding walks, just like Frank, I need to introduce simple random walks. And there's the usual nearest neighbor simple random walk, but I also want to consider more general step sets than just two nearest neighbors. So we'll use the abbreviation SRW for simple random walk, and there'll be the nearest neighbor model. So there's a step set. Omega is the set of all x in ZD which are neighbors of the origin. But I also will want to consider at times the spread out model, because it's convenient often in what I'm going to be talking about to have a small parameter around. And one useful small parameter is often the degree of the underlying graph. So in high dimensions, the degree of ZD is 2D. Each vertex has 2D neighbors. But in the spread out model, we're going to take a bigger set, and the steps will take values in this set omega, which will be the set of all x in ZD, which is an x whose L infinity norm, so the maximum absolute value of a component of x is less than or equal to some number L, which typically we would like to take to be rather large. So then we can define an n-step simple random walk, as you would expect. My simple random walks, unlike Frank's, are called omega, to add to the confusion. So omega is a sequence, omega 0, omega 1, up to omega n, with each of these omega i's in ZD. Usually we start them at the origin, although that one may be relaxed from time to time. And the steps take values in this set capital omega. So omega I plus 1 minus omega I is going to be an element of omega. So in the nearest neighbor model, that just says you move from your current location to a neighboring vertex. But more generally, for the spread out model, you may take a longer step. Now, for a self-avoiding walk, we've seen the definition already, but I'm going to define it slightly more generally, not just because I'm allowing for the more general step set, but because I also want to consider the weakly self-avoiding walk at the same time. So let's suppose that we're given a simple random walk. And then we'll define UST. So S and T are elements of 0, 1 up to n. And this will depend on the walk, omega. And it will be minus 1 if omega of S is equal to omega of t, and it'll be 0 otherwise. Okay, so if the walk happens to be at the same place at times S and t, then this u will take the value minus 1, and otherwise it'll take the value 0. And then we fix a parameter lambda, which is in the interval 0, 1. And we'll define Cn, which depends on lambda, and it also depends on x. So x is a point in ZD here. And I want this to be the sum over all walks omega, simple random walks. So this script W set denotes the set of all simple random walks of length n, which go from 0 to x. So I'm summing over all of those paths. And then I'm going to put in a product over pairs s less than t in the interval 0, n of 1 plus UST of omega. And I'd like to multiply that u times lambda. So what this product does is it gives a weight to simple random walk paths. And that weight is going to be a factor of 1 minus lambda for every self-intersection that the walk makes. So every pair of times s and t where the walk is at the same place is going to introduce a factor 1 minus lambda in the weight. So more self-intersections means less weight on that path. Now you can write this more in the form of a partition function for a Gibbs measure, the way that Frank was writing it, by noticing that this is the same thing as summing over all paths from 0 to x, simple random walks, of e to the minus g times the sum over s less than t of UST of, well, let's say delta omega s omega t. That's the Kronecker delta that takes the value 1 if omega s is equal to omega t and otherwise is 0. This is just an identity that's easy to check if we set g to have the right value, which is the log of 1 over 1 minus lambda. So it's a very simple exercise to check that we have that different way of writing the Cn of x. Now, the case of lambda equals 1 corresponds to this weight factor being equal to 0 whenever there's a self-intersection. So a single self-intersection will give us a factor of 0 here. That'll kill the entire term. And it's only the self-avoiding walks that remain. This corresponds to the taking g to be equal to infinity. So if g is equal to infinity, then as soon as you have a single self-avoiding, as soon as you have a single self-intersection here, the contribution will be killed if g is equal to infinity. So lambda equals 0. The case of lambda equals 0 just recovers the simple random walk for us. The case of lambda equals 1 is the self-avoiding walk, the strictly self-avoiding walk, where no self-intersections are permitted at all. And the case of lambda in between is what's called the weakly self-avoiding walk, where self-intersections are permitted, but they have this probabilistic penalty for the weight of the walk. Here I'm focusing on what happens when the endpoint is fixed, so the walks are going from 0 to x. Sometimes we don't care where they end up, and so we'll define also Cn, which will depend on lambda as well, to be the sum over x in Zd of Cn of x. So for lambda equals 1, this is the number of n-step self-avoiding walks. So Cn1 equals the number of n-step self-avoiding walks. And this is something that we're going to be quite interested in. For the case of 0, lambda equals 0, it's just the number of n-step simple random walks. Because lambda equals 0, there's no interaction. We're just counting the number of n-step simple random walks. Each step is drawn from this set capital omega. And so the number of n-step simple random walks will just be the cardinality of omega raised to the number of steps. So the value of this is the cardinality of omega to the power n. The value of Cn1 is something that I want to talk about a lot. And it brings us to the topic of the connective constant. Now, the connective constant is telling us something. It's basically what do we replace this cardinality of lambda by when we go to n-step self-avoiding walks. I mean, it's reasonable to expect that at least on a crude level, there should be some exponential growth in the number of walks as n increases. So the connective constant is going to be telling us what the base of that exponential growth is. But first of all, we have to prove that there is exponential growth. And that comes from a subadditivity argument, as Frank was explaining. And the subadditivity argument works not just for the strictly self-avoiding walk, but also for the weakly self-avoiding walk. And I would like to just indicate why that's true. Now, I haven't spent enough time in Switzerland to master the wet cleaning, so I'm going to try this cloth and see whether it works. So how does the subadditivity work? Well, it's pretty simple. If you look at all the n plus m step self-avoiding walks, and now I'm not fixing the endpoint, I'll write an inequality, which is actually easy to see. So I'll sum over all omega walks of length n plus m that start at 0 and end wherever they want to. And then I'm looking at this product with n plus m instead of n here, and every factor is less than or equal to 1. Right? Each factor is either 0 or 1 minus lambda. So it's less than or equal to 1, and so if I omit some factors, I'll have an upper bound. And so the factors that I want to omit are the ones which link the first n steps to the last m steps. So I can write this as the product over s less than t less than or equal to n of 1 plus lambda ust. Ust depends on omega, but I'll omit that often from the notation. And then I'll have the product over s prime and t prime between n and m plus n of the same factor. And so I've just left out factors that link s's from this time interval to t's in that time interval. And now what I can do is this gives me some independence. You see, here there's no longer any interaction in this upper bound between what happens in the first n steps and what happens in the next m steps. They're interacting, those two pieces of the walk are interacting on their own, but not together. And so I can split this omega up into two parts, the first n steps and the rest, and then that leads me to this inequality that Cn lambda, Cm lambda is an upper bound. And so this is the basic inequality that is obeyed. And if we take logarithms now, then we get a subadditive sequence. So the log of Cn plus m is less than or equal to the log of Cn plus the log of Cm. And this inequality is very basic. There's a lemma that says that if you have a real sequence, A1, A2, A3, and so on, and you have An plus m is less than or equal to An plus Am for all n and m, then the limit as n goes to infinity of An over n exists. not only that, but it's equal to the nth over all n greater than or equal to 1 of a n over n. As Frank mentioned, it's possible that the limit will be minus infinity, but that's not going to happen in the cases that we're interested in, where we typically have a lower bound like a n greater than or equal to 0. So this is very basic. As Frank pointed out, there are extensions of this to the situation where the a n's are random variables. This is the most plain vanilla version of the subadditivity lemma. And you can see a proof of that in the tutorial today if you've never seen it before. Anyway, we want to apply this to the case where a n is equal to this logarithm. So we'll apply the lemma. And we get that the limit as n goes to infinity of the log of Cn divided by n is equal to the nth of the log of Cn over n. And this limit will be denoted as mu sub lambda. And the case of lambda equals 1, mu is called the connective constant. Well, it's easy to rewrite this equation. Actually, I want this to be the log of mu lambda, because I want to take exponentials now on both sides. So this will be the definition of the log of mu lambda. And now we take exponentials. And so what this says is that mu lambda is equal to the limit as n goes to infinity of Cn lambda to the 1 over n. So that's the exponential growth rate of the number of paths that we were interested in a little while ago. And moreover, if you think about what this infimum is saying, you see that Cn lambda is actually greater than or equal to mu lambda to the n for all n greater than or equal to 1. So you get not just the existence of the limit, but there's also a lower bound on the number of n-step self-avoiding walks that comes for 3. So the special case of lambda equals 1 is the one that I'm most interested in this discussion. So for lambda equals 1, then mu1 is called the connective constant, and I'll tend not to write the subscript 1 when I'm talking about the connective constant. Yeah? What, you mean the 1 over n is out here? Yeah. Oh. Okay, my G was too elaborate. Yeah, thank you. So the first question that you might want to ask about self-avoiding walks once you've seen this subadditivity is, what is this mu? And that's an interesting question. It's not the most interesting question, I think, about self-avoiding walks, but it's definitely an interesting question. And there are some easy estimates that you can write down for the value of mu. So basically what you want is a subclass of self-avoiding walks that you can count explicitly that grows exponentially, and you'd like an upper bound that grows exponentially. So what I claim is that Cn is greater than or equal to d to the n, which is obvious, because if you take steps only in positive coordinate directions in 2 dimensions, if you only take steps east and north, then you can never create a self-intersection. So these are walks. This counts the walks which step in the d positive coordinate directions. There are d to the n of those. They're all self-avoiding. So Cn, I'm talking about lambda equals 1 now, is at least d to the n. For an upper bound, well, 2d to the n is clearly an upper bound for nearest neighbor walks. Let's talk about nearest neighbor walks as well. 2d to the n is clearly an upper bound because that just counts all simple random walk paths. But we can do a little bit better by counting simple random walk paths which are not allowed to make an immediate reversal. So the first step is arbitrary, but then for all subsequent steps you have 2d minus 1 options, not 2d, because you're not allowed to go back where you came from. Here, though, I would be allowed to create a square in this upper bound. So there's 2D options for the first step, 2D minus 1 for the remaining. And so we get this simple inequality. And now if we take nth roots and let n go to infinity, this says that d is a lower bound on mu, and 2d minus 1 is an upper bound on mu. And so mu is, say, between 2 and 3 for the case of the two-dimensional self-avoiding walk on the square lattice. Now, you can do better than this. And there are some rigorous bounds. So for d equals 2 on the square lattice, I'll say what they are. Mu is in between 2.625 and 2.680. So it's 2.6 something. This is a bound of Ponitz and Titman from the year 2000. But it basically is improving on this. We call this a memory 2 walk. So it's a walk which is not allowed to go where it was 2 units of time ago. You could try to rule out memory 4 walks, or rule out squares, rule out hexagons, octagons, and so on, and go as far as you can. I think they actually went to memory 22 here for this bound. And this lower bound is due to Ivan Jensen from Melbourne, who obtained it by counting a subclass of self-avoiding walks called bridges, which we'll hear a lot about next time. There are some pretty precise estimates as to what the value of mu actually is. So Frank alluded to this idea of using exact enumeration. So, if you want to know how many self-avoiding walks there are, one thing you can do is program your computer to tell you how many 0-step, 1-step, 2-step, 3-step, and so on walks there are until you can't do it anymore. It's not so easy to do that, actually. But in Melbourne, Australia, there are some people who have really perfected this to an amazing degree. This is a procedure that started back in the 1950s in London under the influence of Cyril Dome, and Michael Fisher was there, and various other people, including Tony Gutman, who is now in Melbourne. And Ivan Jensen in Melbourne has counted the number of n-step self-avoiding walks on the square lattice up to 71 steps. And there are 10 to the 30 or 10 to the 32, I don't remember exactly. There are really quite a few. And once you know the first 71 or 72 entries in a sequence which is growing exponentially, you can figure out what that exponential rate of growth is. And they're rather confident that it's 2.638158. I don't have my glasses on, so 53031 with an uncertainty of plus or minus 3 in the last, which is the 12th digit. So this is Ivan Jensen, 2003. As we'll hear tomorrow from Hugo, if you do this on the hexagonal lattice, the value of mu is now a theorem that it's the square root of 2 plus root 2, which obeys a quartic equation. And that is that value on the hexagonal lattice was a result in the physics literature by Nienhuis from 1982, and it led people to wonder, including Gutman and company in Melbourne, whether on the square lattice this number might also be the root of a quartic equation. Actually, they wondered it quite a while ago before they knew so many digits. And so they programmed their computer to look for a quartic equation with reasonably small integer coefficients that had this as the root. So this led to a kind of a mystery, which is mu a root of the equation 581x to the 4th plus 7x squared minus 13 equals 0. Those were the smallest coefficients they found, that the value of mu in whenever it was 1989 or so that they had, where they knew it kind of up to here. And it worked. So this equation worked. Then they found more digits, and it still worked. They have no basis for this equation other than, it works. But there's no explanation as to why it ought to be true. And then they found more digits. And now Jensen is, in this paper 2003, is casting a little bit of doubt, because he says that the last digit fails the test, within this uncertainty. But this is a subjective uncertainty. So there's a mystery there. He says probably not in that paper, or at least he's raising a bit of a flag that this might not work. There's another reason, which is that the way that they analyze the series that arise from these sequences makes use of singularities of the underlying generating function, not just on the positive real axis where the critical value is, but also other singularities. This one has a singularity on the negative axis, and they don't see that in their numerics. So maybe not. But there's a theorem, which is what Hugo is going to tell us about tomorrow, Dumenil, Copin, and Smirnov. We heard a lot from Stas Smirnov about related things in other models last week. That says that on the hexagonal lattice, in 2 dimensions, mu is equal to the square root of 2 plus root 2. So this will be the topic of Hugo's lecture on Tuesday afternoon. Now, Harry Keston worked on this self-avoiding walk problem in the early 60s, and he wrote a couple of papers that were quite memorable. And he proved the following, that the limit as n goes to infinity of Cn plus 2 over Cn is equal to mu squared. So Cn is supposed to be growing exponentially like mu to the n, so this is pretty reasonable. But there could be lots of correction factors that get washed out in that limit when you take the nth root. Lots of things to the power 1 over n go to 1 as n goes to infinity. And they could spoil this, but they don't. But there's something kind of unsatisfying about this theorem in that this is a 2 and not a 1. You would rather have Cn plus 1 over Cn converges to mu as n goes to infinity. But that's an open problem still. At least in low dimensions. So in dimensions 5 and higher, this has been proven, but in dimensions 2, 3, and 4, it remains an open problem. So it gives you an idea that this is a tricky problem. This is a tricky model. In fact, it's not even easy to show that the sequence Cn is monotone, that there's more n plus 1 step self-avoiding walks than n step self-avoiding walks, or even as many. It's easy to show that there are more n plus 2 step self-avoiding walks than n step self-avoiding walks. Because if you have an n plus 2 step self-avoiding walk, an n step self-avoiding walk, you can find some extremity of it and then erase a bond and add a little U-shaped thing sticking off of it, which will give you an n plus 2 step self-avoiding walk from an n step self-avoiding walk. And so you can prove that easily that if you only look at every second element along the sequence, that it'll be monotone. But this doesn't work for adding 1 step. If you were on the triangular lattice, it would work, but we're on the square lattice here, or another bipart lattice in higher dimensions. One thing that you can look at, and this was done back in the early days when people started studying self-avoiding walks in the late 50s, Fisher and Sykes asked about the behavior of mu in high dimensions. And they studied an expansion as the dimension goes to infinity of mu in powers of 1 over d. So there's 1 over d expansions. So I'm talking about the nearest neighbor model here. And so there's a theorem that Hara and I proved in 95 that says that there exists a sequence of integers such that as a function of the dimension, mu has an asymptotic expansion to all orders of the form n equals minus 1 to infinity of ai over 2d to the I. So it starts at minus 1 because the leading behavior is 2d. Mu d starts as 2d and then 2d minus 1. So thank you. Yeah, so mu d is equal to, well, it's asymptotic to 2d minus 1 over 2d squared minus, and so on. So actually, these first three coefficients were found by Keston at the same time that he was studying this business over here in the early 60s. But subsequently, it's been shown that there's an asymptotic expansion to all orders. And now, actually, the first 13 coefficients are known. And they're exploding. So the coefficients are getting bigger and bigger like a factorial. At least it looks like they're behaving as a factorial. For a while, Hara and I tried to prove that they were all negative integers, but I'm glad we didn't succeed because actually the 12th and the 13th turn out to have a positive sign in front. And so you can ask then, what can we do with an expansion like this? Now, as often happens with asymptotic expansions, they do remarkably well if you truncate them at the right place. So the rule of thumb that I would use for an asymptotic expansion is that as soon as you plug in your value of d, like 3 here that you're interested in, d equals 3, and as soon as these terms start to get bigger instead of getting smaller, you should stop and throw those bigger terms away. It does remarkably well. It's within, I forget exactly how many, 5% or something in dimension 3 if you do that. And you can ask, can I somehow recover the value of mu of d from this sequence, maybe even seeing what it is as perhaps an analytic function of the dimension? As I said, the coefficients seem to be growing like factorials, which is usually bad news because it means that you have a power series with radius of convergence 0. So that's the first question that you could ask. Is the radius of convergence equal to 0? Don't know. Probably. I guess it is, but can't prove it. It doesn't mean that a series is useless if it has radius of convergence 0, because there's a procedure called Borel summation, which allows you to recover the value of the function on the left-hand side from a divergent series, even if the radius of convergence is equal to 0. So is it Borel summable? And the first step in trying to address this question was recently made by Ben Graham. So here's a theorem of Ben Graham from this year that gives Borel-type bounds for these coefficients. So let's write ZC to be 1 over mu. Then this behaves like the sum I equals 0 to, let's say, n equals 0 to infinity of some other coefficients that are related to those a's and easily calculable from those a's, like that. Then what he proved is that there exists a constant, c, such that for all dimensions, the difference between zc and the first n minus 1 terms, actually this starts at 1, so alpha I 1 over 2d to the I, it bounds this distance, this difference by a factorial. So there's constant to the n times n factorial over 2d to the n. So this is the type of estimate that you would need in order to prove Borel's summability, but unfortunately you need it in the complex plane. So you would need to have a bound like this that worked for, this is the complex 1 over 2d plane, that works in a disk which is tangent to the origin in the right half plane. Well, so far no one has figured out how to do that. But this is the first step. Okay, so that's pretty much what I wanted to say about the connective constant. And now I want to say something about critical exponents. So Frank talked a little bit about critical exponents for the mean square displacement. We'll come to that later. But first I want to talk about critical exponents for mu and Cn. So here's the prediction. I like this term prediction that has been used over the last 10 years instead of conjecture, because it's kind of silly. I feel silly to call these things conjectures because they're true. It's just that we don't know how to prove them. So prediction is a word that's used for theorems whose statements we know but whose proofs we don't know. So here's what it is. Take any lambda between 0 and 1, leaving out 0. Okay? I don't want to talk about simple random walk here, but weakly self-avoiding walk or strictly self-avoiding walk. Then the prediction is that Cn lambda is asymptotic as n goes to infinity, with lambda fixed to some amplitude that depends on lambda, mu lambda to the n, times n to a power which is written gamma minus 1. And I said that mu is interesting, but not the most interesting thing. I think gamma is more interesting than mu, because there's no lambda subscript here. The gamma is supposed to be the same for all values of lambda strictly greater than 0. This is universality. So mu is not universal, the amplitude is not universal, but gamma is universal, and its values depend on the dimension. So it's equal to 1 for d equals 1. Well, d equals 1, as Frank pointed out, for the strictly self-avoiding walk is nothing to talk about, really. You go left or right, that's the end of it. So there's two strictly self-avoiding walks, and the connective constant is 1, and gamma is equal to 1. There's no polynomial. But it's not so easy to show that this behavior holds for the weakly self-avoiding walk. So if lambda is positive but not equal to 1, then it's another story. I'll say something about that later on. But this part is okay. This is proved. For the case of d equals 2, gamma is supposed to have the value 43 over 32, which was a prediction of Nienhuis around the same time of the square root of 2 plus root 2 for the hexagonal lattice. That's 1982. And, well, we've heard something about this already over the last 3 weeks for those of you who were here, which is that there's, especially in the lectures of Vincent Beffera, that maybe SLE 8/3 holds the key to that. So I'll say more about that later on, but there's no theorem at the moment that says that gamma is equal to 43 over 32 in 2 dimensions, but there's a lot of evidence that it has to be also nowadays on the mathematical side. For the case of d equals 3, there's numerical work that gives 1.16 ... For example, The result of Jensen of the enumeration up to 71 steps can be used in order to try to calculate what gamma is. There's other numerical methods that are used to study this problem. But mathematically, there's no clue. For gamma in 4 dimensions, it's equal to 1, but with a log correction, in that this asymptotic formula should have on the right-hand side a factor log of n to the 1/4. And so there's no proof of this now, but the renormalization group holds some promise for proving this type of results, hopefully in the future. And for the case of d greater than or equal to 5, the Lace expansion gives this as a theorem. So we could compare what happens for simple random walk. Cn0 is just equal to, well, for general situation of spread out or nearest neighbor walk, the cardinality of the step set to the power n. There's no polynomial correction, so gamma is equal to 1 in that case. And what we're seeing here is that in dimension 5 and higher, the self-avoiding walk is behaving like the simple random walk does, and it's sort of doing it in 4 dimensions except for some logs, and then something different happens in the lower dimensions. Now, there's a probabilistic interpretation for what this gamma is. Actually, up until now, there hasn't been any probability. We've only been counting paths. That will come a little bit later, but here's a probabilistic interpretation for gamma. Let's look at the probability that 2 n-step self-avoiding walks starting from 0 avoid each other. So let me draw a picture of that. That's going to be a fraction where in the denominator we'll have, let me get some colored chalk here. We could represent the denominator by a line like this and a line like this, where these lines are supposed to represent the number of n-step self-avoiding walks, blue walks or white walks, and the walks are allowed to intersect each other. And in the numerator, I want to count the number of ways that the 2 n-step self-avoiding walks from the origin can manage to avoid each other. And if I just move the origin from the bottom of these pictures to the top left, then the numerator can be represented as the number of 2 n-step self-avoiding walks, and the denominator is the number of n-step self-avoiding walks squared. And then if you plug in that asymptotic behavior that Cn is growing like a constant times mu to the n times n to the gamma minus 1, you get an extra n to the gamma minus 1 in the denominator compared to what you had in the numerator. And so this behaves like some constant, which depends on, well, various things. But the n dependence is in this 1 to the n, 1 over n to the gamma minus 1, that the exponential growth cancels out in the top and the bottom. All right, so we've seen what the prediction is. Yes? This? Yes. It's here. No, it's an identity. Yeah, so we have this prediction, and we would like to see what can be proved about it. So here's the best bounds that are known now for d equals 2, 3, and 4. In higher dimensions, we have good control. But in dimensions 2, 3, and 4, the situation's not so good. So for free, we got from the subadditivity, I'm talking about the nearest neighbor model now. For free, we got from the subadditivity that Cn is bounded below by mu to the n. Okay, so no one's done any better than that. And then for the upper bound, well, in 2 dimensions, there's the mu to the n, and then there's an e to the constant times the square root of n. So you want n to the gamma minus 1, where gamma is some relatively small number, close to 1. Instead, you have e to the constant times square root of n. So this bound, which has a really beautiful proof, in my opinion, is going to be the topic of tomorrow's class. And this is the Hammersley-Welsh bound. So from 1962. So Hammersley was one of the first mathematicians to ever write down any theorems about self-avoiding walks. He and Morton proved the existence of the connective constant in 1954. And he continued to think about self-avoiding walks and percolation from the 1950s onwards. Welsh is the same Welsh as in RSW theory that we heard about. The paper of Seymour and Welsh is from 1978. This is 1962. But he was thinking about self-avoiding walks at this time. And, well, very shortly after the Hammersley-Welsh paper appeared, Keston got in the game and tried to improve this power square root of n. And he improved it a little bit. So it's mu to the n, e to some constant to the power n, and let me get it right here, 2 over d plus 2 at the cost of a log. So in 2 dimensions, this is square root of n, and the log is worse. But in higher dimensions, the power is getting smaller, and you don't care so much about the log. So this is progress. And at that time, he was very interested in what's happening as the dimension gets extremely large. And then you can see at least that this power is beginning to disappear as d goes to infinity, maybe taking us closer to a polynomial. Upstairs. I find it kind of amazing that no one has done better than this in the last 50 years. It's so far from what the prediction is. Someone needs to have a good idea. It's not likely that these methods that were used to prove these bounds are going to improve this, really. I think Keston had to work pretty hard to improve the square root of n to this power. So someone needs to have a good idea. All right. So that's a number of n-step self-avoiding walks. Then you can ask, if I make all of the n-step walks to be equally likely, and that's the uniform measure on the set of n-step self-avoiding walks, then how far away is the endpoint from the starting point, typically? And that leads us to the mean square displacement. So the mean square displacement is, we'll define, I'll write it like this. So this is an expectation with respect to the uniform measure on the n-step self-avoiding walks that start at the origin. And I'm taking the expectation, I'm taking the variance, okay, of the endpoint. So this would be equal to 1 over Cn. And, well, we could let this depend on lambda as well. I think I'd like to do that. And then we'll sum over all walks in Wn of 0x, the endpoint squared times the weight of the walk, which was this product. Okay, so this is a measure of how far apart is the endpoint from the origin, measured in terms of the distance squared. And there's a prediction for this. Frank talked about this, but I'll remind you. what he said and maybe elaborate a little bit, that if you take any lambda, again, in the interval 0, 1, leaving out 0, including 1, so I'm talking here about the weakly self-avoiding walk and the strictly self-avoiding walk, but I'm not talking about simple random walk, then this mean square displacement should be asymptotic to some amplitude that depends on lambda times the power n to the 2 nu. So the 2 is there just because there's a square on the left-hand side. And this nu is another example of a critical exponent, which is supposed to be universal. That's part of the prediction. And if we did take lambda to be 0, and we're talking about the simple random walk, then this would be a question about the variance of the endpoint of a simple random walk, and that's just equal to n in all dimensions. So this is equal to n for simple random walk. And the prediction for the value of nu is like this. First of all, nu should be equal to 1 for d equal 1. Again, for the case of lambda equals 1, the strictly self-avoiding walk, this is just a complete triviality because the walk either moves to the left or the right in a straight line, and so it's ballistic behavior at speed 1, corresponding to nu equals 1. It's not so easy to prove it for the weakly self-avoiding walk, however. But it is proved. And I'll comment again about that later on. 3/4, as in Frank's pictures, for d equals 2. So again, SLE 8/3 probably holds the key, but it hasn't unlocked the door for us yet on that one. Then numerical results give us 0.588 for d equals 3. There was a prediction back in the very early days, in the late 40s, I guess, of Paul Flory, who was a chemist studying polymers and modeling them with self-avoiding walks, who found the value 0.6 here for nu. So it was believed for a while to be equal to 0.6, but that's not consistent with the numerical data or with other theoretical computations in physics which are giving this value rather than 0.6. Should be 1/2 for d equals 4, but again, as was the case over there for Cn, there's a logarithmic correction, and the logarithmic correction to the mean square displacement is log of n to the power 1/4 again. But that's for the square, so it's actually a log to the 1/8 for the typical distance. Typical length scale would have a log to the 1/8 in it. And so renormalization group may help us out there, but we're not there by any means yet with that. And then in high dimensions, d greater than or equal to 5, we get 1/2. And the Lace expansion has proved that. Yes? Oh, yeah, thank you. I just want Wn. Yeah. All right, well, I told you the situation for Cn as far as rigorous results are concerned. Nothing's happened for 50 years in low dimensions, so what about mean square displacement? It's kind of worse in a way because there was nothing 50 years ago and there's nothing now. So here's an open problem. Prove one of the following two bounds. So mean square displacement. Okay, so an obvious upper bound is that in n steps you can only go distance n. So n squared is an upper bound that comes for free. So please try to improve that. And there's also an obvious lower bound, which is that self-avoiding walk is not allowed to go where it's been before. So it has to go away from the origin more quickly than a simple random walk, which is not constrained to avoid where it has been before. But actually, that hasn't been proved. So prove this. Or here's something else you could try to prove if you find that too hard, which is that the endpoint of a self-avoiding walk of length n typically should be at least as far away from the origin as the radius of a ball of volume n. Doesn't make any difference in 2 dimensions in this one, but it does make a big difference in higher dimensions. So either one of those would be progress. There's a theorem of Madras which is unpublished, which does give one lower bound, which is that the mean square displacement is bounded below by a constant to the power n over n to the 4 over 3d. Something, at least it goes to infinity. All right. Okay, so that's the mean square displacement. So there's 2 sequences that are of major interest in this subject. There's Cn, the number of n-step self-avoiding walks, which grows exponentially, and the mean square displacement. And there's a third player, which is the 2-point function. This is really a combinatorial problem, the self-avoiding walk. There's probability theory in the sense that we've put this uniform measure on the set of n-step self-avoiding walks, but it's an exercise to show that the sequence of probability measures that you get is not consistent. Actually, that will be discussed in the tutorial today. And so the self-avoiding walk is not a stochastic process, which means that a lot of your favorite techniques for studying stochastic processes, you can't use them here. On the other hand, it's a very combinatorial problem because we're counting paths. And in combinatorics, when you're doing enumerative combinatorics, you often want to introduce a generating function for the sequence, which is counting the objects that you're interested in. And that's what the 2-point function does. So the 2-point function is defined as follows. So for z, a parameter z, which typically for us is going to be real and positive. It could be complex. Sometimes we want to take it to be complex, actually. Gz of x is the sum over n of Cn of x, z to the n. Let's just talk about self-avoiding walks for the time being and not worry about decorating formulas with lambdas for the weakly self-avoiding walk. So Cn of x, what it is it's counting the number of n-step self-avoiding walks that start at 0 and end at x, and we're forming the generating function from that sequence. So we'd like to study its behavior. Another related quantity is the susceptibility, which gets its name because it's very analogous to the susceptibility, the magnetic susceptibility in the Ising model. And it's defined as chi of z is the sum over all x in zd of gz of x. And if you sum this series over x, then you're just forgetting about where the walk ends in Cn of x. And so the sum of Cn of x over x would be Cn. And so this is just the generating function for the sequence Cn, which is also something that we would be very interested in. Cn0 is delta n0. Now, you can ask about the radius of convergence of this. Cn of x is certainly less than Cn, which is growing like mu to the n. So the radius of convergence of this series is going to be at least 1 over mu. In fact, it turns out it's equal to 1 over mu, and if I have time tomorrow, that's one of the things that I'd like to show. So this has radius of convergence is equal to 1 over mu, which we'll call ZC, the critical value of Z, which plays a role like PC does for percolation. And in fact, this 2-point function plays a role like the 2-point function for percolation, which is the connection probability, the probability that 0 is connected to x when the bond density is p. Here z is like p. Now, these two-point functions, they tend to decay exponentially when the parameter is subcritical. And that's true here. So this will be the one thing that I'll prove today. So proposition, for any z in the interval 0 zc, not including zc, gz of x decays exponentially in x. So the proof is actually quite easy. And it follows from, so we're interested in what happens when x is very far away from the origin. We'd like to show that this is exponentially small in that distance. And the thing that's going to help us with that is the fact that this series is going to start rather late in life if x is far away, because in order to go a distance x, you have to take at least that many steps. So Cn of x is equal to 0 if n is less than the infinity norm, not the infinity norm, the L1 norm of x. You have to get there. So you have to at least take as many steps as the shortest path. So what that means is that this series actually doesn't really start at 0 if x is large, but it starts at this value. Gz of x is less than or equal to the sum, well, it's equal to, I guess, the sum from L1 norm of x to infinity, Cn of x times z to the n. And now the x has done its job, so we can just throw away this Cn of x and replace it by Cn. Which seems maybe like we're giving away a lot, but we have it to give. So then, what I claim is, and this is obvious, that for z less than zc, which by definition is 1 over mu, let's fix such a z, and we'll choose an epsilon now, such that theta, which is z times mu plus epsilon, is less than 1. I can do that. If I have such a z, I can pick an epsilon. It will depend on the z, but that's OK. Then we know that Cn to the 1 over n converges to mu. That was the definition of mu. The connective constant was the exponential growth rate of Cn as n goes to infinity. So from this, there exists a k, which depends on epsilon, such that Cn is less than or equal to that constant times mu plus epsilon to the n. The fact that mu is the limit of Cn to the 1 over n just gives us this bound. And this will be true for all n. So now we can substitute that inequality into the upper bound that we have for gz here. So gz of x is less than or equal to the sum from the L1 norm of x to infinity of a constant times mu plus epsilon times z to the power n. But this is the thing that, excuse me, that we called theta. It's less than 1. So we have a kind of a geometric series here. It is a geometric series. The ratio is less than 1. And the first term is the one that counts. So this is less than some other constant times theta to the L1 norm of x. Theta is less than 1, so that is exponentially decaying. So the two-point function decays exponentially when z is less than zc. All right. So a lot more is known about the behavior of the two-point function for z subcritical. For example, it's known that there exists a norm on RD. Let's call it like absolute value symbols with a subscript z, because the actual norm will depend on z, such that m of z, which is defined to be minus the limit as x goes to infinity of the log of gzx over that norm, exists. So this is for z in 0zc and is a finite positive number. So what this is saying is that gz of x is somehow behaving like e to the minus x divided by xcz, where xc is the correlation length. It's the reciprocal of this exponential decay rate. So it's called the correlation length. And actually, a lot more refined things are known than this that go by the name Ornstein-Zernicke decay. Dima Yaffe, who's here, is one of the people that has been involved in proving this kind of Ornstein-Zernicke behavior, not just in this model, but in many other models. But I think I don't have time to go into that today. This correlation length is real analytic, and it goes to infinity as z approaches zc. So theorem is that chi of z goes to infinity as z approaches zc from below. And well, there's a prediction for this as well, which is that in fact, chi of z behaves like a constant times 1 over 1 minus z over zc to a power which nu, which is that same nu that showed up in the mean square displacement. So it's typical in these models that there's one length. Whenever you measure a length scale which is going off to infinity in some way near the critical point, then it's characterized by one exponent, and this is the exponent nu. Okay, so the exponential rate of decay of the two-point function is going to 0 as z goes to zc. So what is actually happening to gzc of x? When you're sitting at the critical point, how does this behave? Well, the prediction is that there's no more exponential decay, but instead there's power law decay. And that decay is of the form constant times 1 over x to a power, which is traditionally written as d minus 2 plus eta. Eta goes by the name of the anomalous dimension. And moreover, these exponents that we've introduced, so this eta is supposed to be another universal critical exponent. Now we have 3, gamma for the sequence Cn, the polynomial part of the sequence Cn, nu for the correlation length or the mean square displacement, and eta for the critical two-point function. These exponents are not predicted to be independent of each other, but they obey a scaling relation called Fisher's relation, which is that gamma is 2 minus eta times nu. Yes? Here. Well, I'm taking this norm. Yeah, right. I mean, of course, if I multiply this norm by 2, then I'll multiply m by a half and multiply, yeah. I'm going to fix this norm. And then I'll use it to define the correlation length. Now, there's a kind of what I'll call a rule of thumb that relates exponents for generating functions to exponents for sequences. So forget about self-avoiding walks for a moment. This is just a general fact about sequences. Suppose I have a sequence an, say non-negative, that behaves like 1 over r to the n times n to a power gamma minus 1 as n goes to infinity. Like Cn, for example, with r equals 1 over mu, Zc. So if this happens as n goes to infinity, then there's a kind of an if and only if, except it's not a theorem, it's a rule of thumb, which means that, if you're lucky, it probably holds in your situation, that says that the generating function that you form from this sequence will diverge at z equals r, and the way that it diverges depends on this gamma, that there's some constant, and then you'll have 1 minus z over r actually to the power gamma. Going in the forward direction here, this is called an Abelian theorem, is relatively easy. So if you know the behavior of your sequence, then you can figure out the behavior of the generating function. To go in the opposite direction is less straightforward, because if you don't know something about the regularity of your sequence, it might not be true. An might decide every once in a while, after huge gaps as you increase n, to do something stupid. An might take on some crazy value every once in a while, but very rarely. Then you'll never see it in this generating function, but unfortunately you would see it here. It would spoil this. So you need usually some regularity in order to go backwards, and those types of theorems go by the name of Tauberian theorems. And in the tutorial today, you'll see one version of that. And so if we apply that rule of thumb to the susceptibility, which is the generating function for Cn, then we have a prediction for how the susceptibility ought to blow up at the critical point, which is that chi of z ought to behave like some constant times 1 minus z over zc to the power minus gamma. And this is as z approaches zc from below. In case of 4 dimensions, the prediction would include some logarithmic correction. There's a log here, and that would translate to a log over there. All right, so just about 10 minutes left. And in those 10 minutes, I'd like to say something about what's known, a little bit more about what's known or what the prospects are for these various predictions that I've been talking about. Let's start with d equals 1. So we've already noticed that for the strictly self-avoiding walk, there's nothing to talk about. But for the weakly self-avoiding walk, it's not so easy. And there's a theorem of Graven and Den Hollander from 1993, I guess. And Wolfgang Koenig, who I guess is speaking sometime this week, from, was it a year later? No, 3 years later, 1996, for the weakly self-avoiding walk, which basically answers the main questions for the weakly self-avoiding walk, and shows that it's in the same universality class as the strictly self-avoiding walk, no matter how small the penalty is for the self-intersections. So it says for any lambda strictly between 0 and 1, there exists a speed, theta of lambda, which is in 0, 1, and a standard deviation, sigma lambda, which is between 0 and infinity, such that if you take the limiting probability with respect to this measure Qn, so this is the weakly self-avoiding walk measure with parameter lambda. I guess I already gave that a name, didn't I? We called this En lambda. So, but I'm taking the probability, not the expectation, that the endpoint of the walk, so this would be omega n minus theta n divided by sigma root n, the probability that that's less than a constant. So essentially what we're looking for is a central limit theorem for the absolute value of the endpoint. The absolute value is there because there's sort of different behavior for the walk going left or right, and we don't want factors of a half that deal with that. So this converges to a normal. As n goes to infinity. So in particular, what this is saying is that the endpoint is growing linearly with speed theta, and that the fluctuations around that endpoint are normal fluctuations. Okay, so that's d equals 1. Basically, we know the answer. For d equals 2, there's this promise of SLE, 8/3, which many of us heard Vincent Beffera and other people talk about over the last 3 weeks. There's a theorem of Lawler, Schramm, and Werner that, roughly speaking, says that if the scaling limit of the two-dimensional self-avoiding walk exists and obeys a certain conformal invariance property, then it must be SLE 8/3. But at present, we don't know how to prove that the scaling limit exists, and therefore we also don't know how to prove that it has the conformal invariance property. And so there's a question mark here, or at least there's lots to think about. There's also Monte Carlo experiments that have been performed in the case of 2 dimensions. And there are the exact enumeration that I've mentioned. All of these things confirm the predictions. So there's really no doubt that the predictions are true, but we just don't know how to prove them. For d equals 3, it's really wide open. I mean, we don't have a candidate for what the scaling limit should be. There's no stochastic process or no mathematical object that we know that should be the limit. So there's no rigorous results. I've told you how bad the bounds are on the mean square displacement. Here the Monte Carlo and the exact enumeration are particularly important. I mean, they're important already in the case of 2 dimensions in order to confirm the predictions of Nienhuis. But in 3 dimensions, there is no prediction that says that gamma is the solution of some equation or that it's some rational number. We just don't know what it is. And so the numerical methods are important in order to try and actually get it as accurately as we can. And the best way of doing that, for example, for nu, is using Monte Carlo. And Nathan Klisman in Melbourne is just this year published a paper where he's simulating walks of length 33 million and knows nu to several digits using those calculations. For d equals 4, there's rigorous work on the renormalization, using renormalization group methods for a continuous time weakly self-avoiding walk. So that's something that I'm going to talk about at the end of the course. But there, with bridges, we've shown that the critical 2-point function behaves like 1 over x to the d minus 2 as x goes to infinity. In other words, that eta is equal to 0. And for d greater than or equal to 4, there's the lace expansion, which was introduced first by Bridges and Spencer back in 25 years ago. And Hera and I, in 1992, showed that it can be applied to the strictly self-avoiding walk in dimensions greater than or equal to 5. And so that's what I'll be talking about on Wednesday and Thursday. OK, so I'll stop here. Thank you very much.